We'll now begin section 5.4, where we will be talking about properties and applications of logarithms. We'll begin with an example that will get us ready to discuss the properties of logarithms. Our example reads, Anne reads an ad in the paper for a new bank in town. The bank is advertising continuously compounded savings accounts. All right, so right now I already know that if we are talking about interest that is continuously compounding, remember that from the last section, we know that we are talking about a formula. A is equal to P times E raised to the RT. So the bank is advertising continuously compounded savings accounts in an attempt to attract customers, but fails to mention the annual interest rate. Curious, she goes to the bank and is told by an account agent that if she were to invest $10,000 in an account, okay, so if this is her initial investment, remember this is your P, her money would grow to $10,202.01. So this is her final amount. This would be her A. In 1 year's time, so here's our T. But strangely, the agent also refuses to divulge the yearly interest rate. What rate is the bank offering? And so we need to determine the interest rate. So we can set up the interest rate for this problem, or set up the formula for this problem, and then solve for the interest rate. So if we set up what we know into our formula, plugging the A in, is equal to the P, E to the R times the time, which is 1. So we have a formula that looks like $10,202.01 is equal to 10,000 times E raised to the R times 1. So as we go to solve this problem, let's look at what needs to happen. All right, here's our formula that we've already written down. So we're at that point right now. We know that R times 1 is going to be R, and so that's all that's happened here. We need to convert this to logarithmic form, which we know how to do. Remember that if we want this written in log form, that we would write down the word log, and our base would go here. So our base in this expression is going to be E. Remember, your exponent goes on the other side, and then the number that's left goes in the middle. And so 1.020201 would sit right there. Remember, log base E is the natural log. And so that's how we have this statement. The natural log of 1.020201 is equal to R. And then we can plug into our calculator and get an interest rate of 0.02%, or 0.02, which is roughly 2%. And so we can use the natural logarithm since the base is E, and we can solve that equation for R as we did. Okay, so no problem with something like that. Let's look at a second example. Solve the equation 2 to the x is equal to 9. So in order to solve this, we can convert it to log form, but even if we do that, as we saw in the last example, even if we do that, we're not in any better shape. So if we write down the word log and find our base, what's our base here? Our base is going to be 2. Remember, your exponent goes on the other side. And then the 9 goes in the spot that's left. And the problem is that the calculator does not evaluate a base 2 log. And so we can't figure out what that's equal to as an exponential equation or as a logarithmic equation. So our ability to work these log problems is still incomplete. And so in this section, we're going to talk about some properties of logs that would allow us to solve some of these more complicated equations. And so let's look at what those properties look like. And we've got 3 that we're going to focus on. One of those properties says that if we're taking the log base A of x times y, that's equivalent to log base A of x plus log base A of y. So what you want to remember here is that if you have a multiplication, that you can break this up and put an addition in between. We also have a property that says log base a of x divided by y is equal to log base a of x minus log base a of y. So in this case, we're saying that if we have a fraction, we can break up the top of the fraction from the bottom of the fraction as long as we put a subtraction sign in between. And finally, our third property says log base a of x to the r is equal to r times log base a of x. So what this tells us is that if we have a problem where we have a power, that power can be pulled down in front of the log. So those are the three properties that we're going to be working with. In our next presentation, we'll look at some examples of how to use those properties.